Welcome back to another explainer. Man, I am absolutely thrilled to get into today's topic with you. We're going to explore the fascinating, perfectly synchronized chain reaction that happens every single time you start your car. It's something most of us do every single day without a second thought. But when you actually stop and look under the hood, it is an absolute marvel of modern engineering that took over a century to perfect. So, let's dive into this. I want you to picture yourself just sitting right there in the driver's seat. You slide the key into the ignition, you give it a tiny twist with your wrist, and you hear that familiar rumble. But what invisible dominoes did you just knock over? How does that small, effortless twist of your fingers magically wake up thousands of pounds of resting metal, glass, and rubber? Well, here is our roadmap for today's journey of power. We're going to cover 1. Turning the key, 2. The 4-stroke cycle, 3. The drivetrain system, and 4. How a differential works. Let's get going. Starting right at the top with Section 1, turning the key and the spark that starts it all. You see, the key is essentially just a simple electrical switch talking to your car's computer. When you slide it in and give it that first click, accessory mode, the engine control unit, or ECU, basically wakes up from its sleep. That's when your radio and cabin lights might pop on. Turn it to the second click, the on mode, and things get serious behind the scenes. The fuel pump whirs to life, priming the fuel lines with intense pressure, and the spark plugs, they go live, just waiting for their moment. Finally, you push the key all the way into start mode against that spring tension. This tells the ECU to engage the starter relay, which then sends a massive, heavy surge of battery power directly down to the starter motor. And this right here is the exact moment electricity becomes physical motion. That starter motor uses the electrical surge to physically swing a small pinion gear outward, meshing its teeth tightly with a massive gear attached to the engine's crankshaft. Now, because the engine is completely dead and resting at this point, it takes a tremendous amount of torque to get it going. The starter motor literally forces the heavy, dormant engine to start spinning. It's wild, just a tiny jolt of electrical energy triggering a massive mechanical reaction to finally wake the sleeping beast under the hood. Which brings us to Section 2, the 4-stroke cycle, or creating the power. Once that starter motor gets things spinning, the engine has to take over. By definition, most cars out on the road today use a 4-stroke engine. This is an internal combustion engine where a piston completes 4 completely separate movements, or strokes, up and down a hollow cylinder, turning the heavy metal crankshaft along with it. Think of it this way. If the starter motor was your blaring alarm clock, this 4-stroke cycle is the engine finally grabbing its morning coffee, getting out of bed, and doing the hard work itself. Let's actually break down the exact sequence of this mechanical heartbeat. First up, intake. The piston drops down in the cylinder, creating a vacuum that sucks in a very precise, misted mixture of air and fuel. Next, compression. The intake valves close and the piston comes back up, squeezing that mixture incredibly tight. The pressure in there just skyrockets. Then, the magic moment. Combustion. The spark plug fires, igniting that highly pressurized fuel. This violent explosion, this is the exact origin of your car's forward power, violently shoving the piston back down the cylinder with tremendous force. Finally, exhaust. The piston rises one last time. An exhaust valve opens, and it pushes all those spent gases right out to the tailpipe. Squeeze, bang, blow. Over and over again, thousands of times a minute, across 4, 6, or 8 different cylinders in perfect harmony. Okay, let's move on and see how this builds in Section 3, the drivetrain system, moving the power. Now, before we go any further down the vehicle, we absolutely have to clear up a super common misconception you'll hear at dealerships all the time. People use the terms powertrain and drivetrain like they mean the exact same thing, but structurally, they are very different. The powertrain is the whole shebang, the engine actually making the power plus the entire system transferring it. The drivetrain, however, strictly excludes the engine. It is purely the group of components, the transmission, the driveshafts, the axles, that carry the rotational force away from the engine to the wheels. And the specific parts of that drivetrain totally change depending on the exact type of vehicle you drive. A manual transmission relies on a heavy flywheel and a physical friction clutch that you control directly with your left foot. An automatic transmission, on the other hand, uses a brilliant fluid-filled casing called a torque converter to do that exact same job without any input from you. A front-wheel drive car compacts all of this into a single unit called a transaxle right between the front wheels. But look, regardless of the specific parts, the ultimate goal is exactly the same. You're taking the wildly fast rotational speed of the engine, which is way too fast for the wheels to handle directly, and using heavy-duty gear ratios to step it down to a usable, manageable speed for driving. If you're in a standard rear-wheel drive car, this means running a long, heavily balanced metal propeller shaft down the entire length of the chassis. It is a massive physical and engineering feat when you really stop to think about it. You're taking thousands of tiny contained explosions at the front bumper, turning them into sheer rotational force, and sending that immense force down a heavy metal rod spinning thousands of times per minute just to push a 2-ton metal box down the highway smoothly, quietly, and efficiently. Which leads us to our final stop. Section 4. How a differential works. Solving the turning problem. Here's a major physical conflict we hit at the very end of our power journey. What happens when this heavy metal box actually needs to turn a corner? Think about the basic geometry of a turning car. The wheel on the inside of the turn is carving a very tight, short circle, but the wheel on the outside of the turn is carving a much wider, longer circle. Here is the massive physical problem. Both wheels are attached to the same car, so they arrive at the destination at the exact same time. If the left and right wheels were locked together on a single solid axle, spinning at the exact same speed, the car would aggressively hop, skip, and slide around every single corner. The tires would constantly scrub the pavement. Smooth turning at high speeds would be physically impossible without snapping an axle or shredding your rubber. So, the crucial point is this. To make a turn without slipping or breaking components, the outside wheel absolutely must spin faster than the inside wheel, period. We need a mechanical component that can take the solid rotational power coming from the transmission and somehow split it dynamically and unevenly between the left and right wheels whenever the car turns. Enter the differential. To solve this deeply complex geometric physics problem, modern automotive engineers rely on an invention that dates back, get this, to the 3rd century AD. No way, right? The differential gearing mechanism was originally invented in ancient China for a device called the south-pointing chariot, which was essentially a mechanical compass vehicle. This was centuries before the very first automobile was ever even conceptualized, yet its elegant, ingenious design is still bolted to the underside of almost every single car on the road today. Inside the heavy metal housing of the differential, there is an incredibly elegant geometry of gears. Let's trace it out. When you drive straight, a large crown gear spins the left and right axles at the exact same speed. Everything is locked in harmony. But the second you turn the steering wheel, these brilliant little inner gears, called planet pinions, begin to rotate and spin around central sun gears. This purely mechanical action allows the incoming rotational speed to be dynamically and unevenly shared between the two wheels, letting the outside wheel speed up while the inside wheel slows down. Furthermore, the differential takes the rotational motion of the driveshaft, which runs parallel down the length of the car, and seamlessly turns it 90 degrees, so it runs perpendicular right out to the wheels. And if that sheer mechanical ingenuity wasn't impressive enough, consider this number, 97. Even with the power traveling all the way from the fiery engine block, through the thick fluid of the transmission, down a spinning steel drive shaft, and through multiple complex gear meshes inside the differential that turn the energy 90 degrees, this entire mechanical system operates at a staggering 94 to 97% efficiency. Only 3 to 6% of the engine's hard-earned power is lost to mechanical friction along that massive journey. It is an absolute triumph of lubrication and precision machining. It really is a symphony of mechanics, isn't it? From the simple twist of a key acting as a tiny electrical switch, to the violent 4-stroke combustion cycle, down the long, heavy spine of the drivetrain, and finally through ancient 3rd century geometry to make you turn a corner perfectly without a sound. Next time you sit in the driver's seat and hit the gas pedal, will you take a second to feel those thousands of synchronized explosions and brilliant mechanical rotations happening right under your feet? Thank you so much for joining me on this explainer today. I really hope it sparked your curiosity as much as it sparked that engine.